Now the topic is network reduction techniques. Means by simplifying the network, if any network, by simplifying the network into simple circuit. Simple circuit means one source and one passive element. To bring the network into simple circuit, after bringing the network into simple circuit, we will calculate the responses like current, voltage, and power across any passive elements. The main aim of these techniques also to find each and every branch current, voltage, and the power. Now here in our syllabus, the network reduction techniques here we are having as series parallel technique and the star to delta or delta to star technique. Now, but the main disadvantage of this technique is limitation is it is applicable to single source network only. It is applicable for single sourced network. If the network is having more than one source, to find the currents already discussed, we are going to using mesh and nodal analysis techniques. Mesh and nodal. So those are called universal techniques. Those are applicable for single source network also. But series parallel technique is applicable for only single sourced network. Now let us discuss about properties of series connection. But what is when we can say the elements are in series? At any node, if two elements are existing, at any node two elements or two branches are connected, then we can say those two elements are connected in series. Means at any node two elements means that node is called a simple node. Simple node. And second property is in series connection, current is same. Because at node if two elements are existing means we can say it's a simple node. If those two elements means we know current, if according to KCL, current entering equal to current leaving. That's why if any elements are connected in series, current flowing through those two elements are same. Those two elements is same. Now voltage division takes place. If elements are in series, voltage division takes place. Node elimination will takes place. The fourth property, node elimination will take place. All these properties will prove with some examples. If n number of equal resistors are connected in series, then we will calculate the total resistance by using formula as R equivalent is equal to N into R. There N is the number of resistors connected in series and R is the resistance magnitude, and R is the resistance magnitude. And sixth property is if n number of elements are connected in series, different resistors magnitudes, n number of different resistor magnitudes are connected in series, then the R equivalent is always greater than the individual resistors which are connected in series. These are the properties of series connection. And properties of parallel connections. Here first property definition. If elements are existing between same nodes, if those are two or more than two existing between same nodes, then we can say those elements are connected in parallel. Those elements are connected in parallel. And second property here, current division will take place in parallel connection. Current division will take place. So now voltage is same here. Voltage in parallel connection, voltage is same. Here there is no node elimination. Simplification purpose, nodes should not be eliminated. Whatever the nodes are existing, same nodes will exist as usually. But in series connection, what we studied, node elimination will take place. If n number of equal resistors are connected in series, if n number of equal resistors are connected in parallel, then R equivalent is equal to R by N, where R is nothing but resistance magnitude and N is nothing but number of resistors connected in parallel. The sixth property, if n number of resistors are connected in parallel, then R equivalent is always less than the individual resistance magnitudes which are connected in parallel. To understand this, let us take one example. We'll discuss. See, one simple circuit I took here, simple circuit, nothing, not simple circuit, one loop I took there. Here two resistors are connected with one voltage source. If you observe here in this network, the number of elements here are 3, and then the number of nodes, there are 3 nodes. between R1V one node, between R1 to R2 another one node, and between R2 to V one node. Then all the nodes are simple nodes. Why? Because at any node only two elements are existing. At any node two elements, then we can say those are connected in series. Those are connected in series. Assume current flowing here is source, some I amount of current from source positive terminal to source negative terminal. Then the voltage across resistor R1 is I into R1, and the voltage across resistor R2 is I into R2. Why? Because here current flowing is same. Because we can say, we are saying all are connected in series. Now if you apply KVL to that loop, KVL will be saying what? Algebraic sum of branch voltage in a loop is 0. See there, if you apply KVL, we can get expression as V is equal to V1 plus V2, where if you brought the network into simple circuit, then we have to bring all the passive elements into one equivalent magnitude. So after bringing the network into simple circuit, we can calculate I is by using formula as I is equal to V by R equivalent. I is equal to V by R equivalent. With this, V is equal to what? I into R equivalent. I into R equivalent. Now V1 is nothing but what? I into R1. V2 is nothing but I into R2. Here in series connection, current is same. So if we simplify both sides current, then we can get R equivalent as R1 plus R2. Means if two resistors are connected in series, the total resistance we can calculate by using formula as R1 plus R2. Here what we studied, in series connection, voltage division takes place. Voltage division takes place. See, if you taken voltage expression across any one resistor, say passive element R1, there V1 is equal to what? I into R1. So we can write this expression as V1 is equal to I is nothing but what? Total current flowing the network. That also we can calculate by using formula as V by R equivalent. R equivalent is nothing but what? Here R1 plus R2. Then we can write this expression as V1 is equal to, if you want to find any branch voltage in series connection, is equal to total voltage in that branch, total source voltage into resistance magnitude which we need to connect to the voltage. Means we are going to calculating voltage across V1. So R1 divided by total resistance which are connected in series, R1 plus R2. Similarly, V2 we calculate by using formula as V into R2 by R1 plus R2. V into R2 by R1 plus R2. Now, if three resistors are connected in series, we can calculate by using formula R1 as R1 plus R2 plus R3. Similarly, V1, V2, V3 also we will calculate across any particular resistor, since in series voltage division takes place. Similarly, resistor and inductive reactance accepts almost equal properties, because those two units are also in ohms. That's why we will calculate inductance, total inductance, if two inductors are connected in series, by using formula as L equivalent is equal to N1 plus L2. Inductive reactance, capacitor are having opposite properties as we discussed previously. That's why there we will calculate, if two capacitors are connected in series, we will calculate total capacitance by using formula as equivalent is equal to C1 C2 by C1 plus C2. C1 C2 by C1 plus C2. Next, proof for parallel connection properties. So here we assume one simple network here, one circuit. A circuit is having three elements, those are connected like this. If we check in this network, the number of nodes here are two only. The number of nodes there are two only. See, at any node, between two nodes, across the two nodes, how many elements are connected? Three elements are connected. Then we can say those three are connected in parallel. The network reduction technique is nothing but we have to bring all passive elements into one total value. So for that we are going to using here parallel connection. Now here, if we apply KCL at any principal node, how many principal nodes are there? Number of principal nodes there are two. Number of nodes 2. Those two nodes are principal nodes. Why? Because at any node three elements are existing. Now if we apply KVL to inner loop that you can get as expression as v1 is equal to v2. If you apply to the outer loop, you can get expression as v is equal to v1. If you apply lower loop, you can get expression as v is equal to v2. Means with this we can say v is equal to v1 is equal to v2. That is in parallel connection. Voltage is same. Current division takes place. With this, we can write formula using as I is equal to I1 plus I2. After applying current across a passive element, I is equal to I1 plus I2. Now, if you apply Ohm's law there, formula I is equal to V by R equivalent. So V by R equivalent is equal to V1 by R1 plus V2 by R2. Voltage same you are saying. That's why you can say R equivalent is equal to R1 R2 by R1 plus R2, or otherwise 1 by R equivalent is equal to 1 by R1 plus 1 by R2. Here what we studied, current division takes place. So take current expression across any passive element. There you can have across R1 I am applying. So I1 is equal to V by R1. V is nothing but what? Total voltage. V by R1, because voltage is same in parallel connection. Now I1 we can write as V is nothing but what? I into R equivalent into 1 by R1. If you simplify, we can get expression for I1 as I1 is equal to I into R2 by R1 plus R2. Similarly, I2 is equal to total current into R1 by R1 plus R2. Similarly, if two inductors are connected in parallel, we can calculate total inductance by using formula as L1 L2 by L1 plus L2. Similarly, if two capacitors are connected in parallel, C equivalent is equal to C1 plus C2. Next, if three resistors are connected in parallel, we can calculate R equivalent by using formula as R1 R2 R3 by R1 R2 plus R2 R3 plus R3 R1. Now come to star to delta or delta to star technique. Same, the purpose of series parallel technique, whatever, the same technique is applicable in star to delta, delta to star technique. But here this technique also applicable for single source network. That too, for a single source network, if elements are not in connected series and not in connected in parallel, then only we have to use this technique. Means this technique is applicable for a single source network if series parallel technique is failed. Just refer formulas how to convert. See, left side is a delta connection, right side represents star connection. Suppose if you want to convert delta to star, means delta means nothing but what you are having. You are having R1 R2 R1 to R2 3. Suppose you assume resistors, each leg resistance values is like this. So common resistors you are going to getting between two nodes resistor. Suppose if you want to know node 1 to node 2 resistance, we have to calculate, start from node 1 go to 2. So you may get R1 R2, similarly R2 R3 R4, or simply you can write R1 2 R2 3 R3 1. If you want to convert into star connection means individual resistance values R1 R2 R3. You have to calculate R1 R2 R3. If you know this R1 2 R2 3 R3 1, then we use formula as R1 is equal to, we use formula as R1 is equal to R12 into R13 by R12 plus R23 plus R31. We use this formula. Similarly, R2 we can calculate by using formula as R12 into R23 by R12 plus R23 plus R31. So like that, if any delta network is there, as per our requirement, we will convert that into star connection. Similarly, if star connection is there, if you want to convert it to delta, we use these formulas. Say if you know resistance is leg resistance values like R1 R2 R3. If you want to calculate R12, we use formula as R1 plus R2 plus R1 R2 by R3, R1 plus R2 plus R1 R2 by R3, R1 plus R2, R1 plus R2 plus R1 R2 by R3. By using this formula, we will calculate delta values. Delta connection definition, star connection definition. Star connection will exist if similar ends are connected together, and delta connection will exist if dissimilar ends are connected together. The importance of star and delta connections studied. The topic is different here. Three-phase circuit we discussed, and this topic is different here. This is about series parallel techniques. We discuss already problems. So practice problems, you can get good knowledge. Main we have to understand here is why we are going to using series parallel technique when we have to use this technique. Right.